In this video, I want to make very slight additions and extensions to the trigonometric identities that we found through e to the I pi in the previous two videos. The double angle identity here with the cosine of 2 theta and the sine of 2 theta, and then the angle sum identities with the cosine of two angles alpha and beta summed, alpha plus beta, for the cosine and sine. And these extensions are the half angle and the angle subtraction identities. And I've written them here in their incomplete forms because we're going to find them in this video. And you can probably match them up. The half angle identities are asking for the cosine and sine of theta over 2. And the angle subtraction identities, very similar again to these identities, is just the cosine of alpha minus beta. Well, let's start with the angle subtraction identity. It should feel pretty natural here that this is very, very similar to the angle sum identity. And with one quick substitution, we can actually put it in exactly the form of this identity. And we can say that substitution, we can remember that the cosine of alpha minus beta is the same thing as the cosine of alpha plus negative beta. And now we have it in this form where alpha equals alpha, and then this old beta, we can call it purple beta equals negative beta. And this is not to be too confusing, but we just have negative beta in its place. So when we plug in betas, we'll be plugging in negative betas. So if we go back to our angle sum identities, we can now plug these in with alpha as alpha, and we're going to be plugging in negative beta because that's what we're passing in. And what do we get? Well, the cosine of a negative beta will just be the regular beta. But sines, because sines are odd functions, the sine of a negative beta will be negative sine of positive beta. So as we look through these angle sum identities, let's keep that in mind. So first we have a cosine of a beta times the cosine of alpha, but those are all cosines, all even functions, so that won't change. So we have the cosine of alpha times the cosine of beta. But now we have minus sine of alpha times the sine of beta, but we're plugging in the sine of negative beta because this is angle subtraction. The sine of negative beta is negative sine of positive beta, so we can make this negative into a positive, say plus sine of alpha sine of beta. The reason that we're plugging in negative beta here is because we're subtracting. We're just rearranging how we're talking about it. We're saying instead of saying the cosine of alpha minus beta, we're saying the cosine of alpha plus negative beta. So we plug negative beta in. Okay, let's do the same thing for the sines now. So we have a sine of beta right off the bat here, and so we know to make this negative. Let's just rearrange it though. Let's look at the second term first. So we have a positive then a negative. So second term, sine of alpha cosine of beta. That doesn't change. So we have sine of alpha cosine of beta. Okay? And now we know, because we have this sine of beta times a positive term, we're going to have a negative here. Sine of negative beta, negative sine of positive beta, right? Okay, so times, or minus cosine of alpha times the sine of beta, which again is the sine of negative beta coming out to negative sine of beta. Now, let's just remove this to make some space for the next identity that I want to talk about, which is the half angle identity. Just like the angle subtraction identity, which is very similar to the angle sum identities, the half angle identity is tied to the double angle identities. And to find the half angle identities, the cosine double angle identity in specific is going to be very useful. So let's just write this down. One other way of thinking about the cosine of 2 theta equals cosine squared of theta minus sine squared of theta is to have there be some other variable, say x, equal theta over 2. Because of this, we can now say, again, just using the double angle identity on this new variable, the cosine of, well, 2x is just going to be theta equals the cosine squared of, well, x is just theta over 2, and minus sine squared, again, theta over 2. you can see we can make the double angle identity. We can force it to have these half angle values. So what we can do now, let's scroll down just a little bit to give us some space here, is we can remember. Now we have two of these half angles. We want to get rid of one. This is a perfect situation because we have the cosine squares and sine squares to make a substitution from the Pythagorean identity. Remember, the Pythagorean identity says if you have a circle, right, and which is what trig functions are all about, you have your triangle, right? So, and it's a right triangle. So the cosine squared, the x value squared, plus the y value squared, sine squared, this is going to equal 1, which is the radius of the unit circle. And again, these x's could be thetas. So if we rearrange this, we find we can make cosine of squared of x equals 1 minus sine squared of x, or sine squared of x equals 1 minus cosine squared of x. And there's a bit of a fork in the road here on which one we want to plug in. Let's start by plugging in this sine squared definition. So we have the sine squared of some value. We have the sine squared of some value. Let's plug it in. So we have the cosine of theta equals the cosine squared of theta over 2 minus, instead of the sine squared of theta over 2, we're now going to say minus 1 minus, just plugging this in here, the cosine squared of theta over 2. Hopefully this makes sense. We just made a substitution straight from the Pythagorean identity, slightly rearranged. Now we have, of course, two negatives, so this is going to become here if we were to erase these parentheses. This is going to be, let's just redraw this. This is going to be a plus, this is going to be a minus. If you remember, distribute the parentheses. So we have 2 cosine squareds, that's going to become 2 cosine squared. So we have, sorry, this one's not squared. The cosine of theta equals 2 cosine squared theta over 2 minus 1. And before we go on to just do some basic algebraic manipulations to get what the cosine of theta over 2 is, I just want to note that this is also a really nice identity to have. And it doesn't have a formal name. It's usually just that identity on the way to getting the half angle identity for cosine, but it's nice to have in your back pocket because it talks about another way to represent the cosine of an angle. Okay, well, on that note, though, let's just find the half angle identity. So we have here, if we add 1, we get the cosine of theta plus 1. And here, if we divide by 2, we divide by 2, and we're left with just that this equals the cosine squared theta over 2. Of course, we can just take the square root at this point, so we can get that the cosine of theta over 2, this half angle identity for the cosine, is, remember the plus or minus square root of this value. Okay, so let's copy this guy up to here. I'll scroll up so we have it here. This is the first identity that we've come up with, the cosine half angle, and I'll make this plus or minus go down a little bit. That's the one thing with copying. You don't quite know where things are going to go. Okay, so now let's scroll back down. Let's think. So this time, last time we used the sine squared. What if instead of replacing the sine squared of theta over 2, we instead replaced the cosine squared of theta over 2? What would be different? Okay, so cosine squared of theta over 2, that's going to get us 1 minus sine squared. Let's just come over here, down into this corner, and start working again. So the cosine of theta is going to equal, well, now we're replacing the cosine squared, so 1 minus the sine squared of theta over 2 minus the sine squared of theta over 2. Again, we're not replacing the sine squared, we're replacing the cosine squared this time. Okay, this time we have no distribution of negatives to do. We just go straight up to the next step, just combines terms. I shouldn't keep on writing that as cosine squared. We have 1 minus 2 sine squared of theta over 2. We're not using the half-angle identity of sine for this. We're just continuing with the cosine half-angle identity. We can do the same thing as we just did here. We can subtract 1, so I'll do it here. We can subtract 1, so the cosine of theta minus 1. Okay, and then we can divide by negative 2. Divide by negative 2. And before we take the square root here, just want to say we can rearrange this also. So we can say this here, this equals 1 minus the cosine of theta, which is how it's typically written, so you're not dividing by a negative thing. Okay, and now that I have this in equation, let's just actually copy this and put it down over here. So we have, sorry for the confusing part, but we have 1 minus the cosine of theta over 2. The plus or minus square root of this is equal to the sine of theta over 2. So it's interesting how both of the half-angle identities take this square root form. But of course it makes sense, because you get them both from the cosine double angle identity, and you get that substitution from the Pythagorean identity. So let's just quickly write this down. This is the plus or minus square root of 1 minus the cosine of theta over 2. Pretty cool stuff. Some pretty natural extensions from the double angle identity, from the angle addition identity. We can get ourselves 4 new trigonometric identities.